Hello students, I'm Dr. Saliha Jamal from Department of Geography, Aligarh Muslim University, Aligarh. Welcome to today's class. Dear students, we have finished with the types of spatial analysis, and now I'm going to take one of the spatial analysis, that is transformation, and I'm going to explain the transformation with some real world examples. So it will be more clear, you will have more clear understanding about what exactly the transformation in spatial analysis means. So let us start today's class, student. Coming to the part when we talk about the transformation, exactly the transformation, we are dealing the transformation in spatial analysis. So exactly transformation in spatial analysis, it deals with the alteration, or we can say some sort of modification in spatial data, which involves maybe changing the shape, size, orientation or position of spatial data sets. Let us explore the different types of transformation with some of the real world examples. There are 5 different types of transformation. So first one is geometric transformation, then we have coordinate transformation, then we have topological transformation, then we have raster transformation, and the last one is attribute transformation. Coming to the geometric transformation. Geometric transformation is exactly, it involves the process of altering, or we can say some sort of modification in shape, size, orientation, or even on the position of the geometric objects or features within a spatial data sets. Means all types of alteration, either we are dealing with the shape, size, orientation, all types of we can say the changes, or we can say the alterations are taking place within the spatial data sets. Coming to, if we take the real world example, here we are going to explain this geometric transformation with satellite image rectification and with georeferencing historical maps. If we talk about the satellite image rectification, actually satellite images are often, I can say, suffer from different types of geometric transformation. When we are students, be clear about this. When I'm talking about geometric transformation, it simply means some sort of changes in shape, size, orientation or position of spatial data sets. So here also, when the satellite images are of, we can say, we generally get the satellite images having different types of geometric distortion. There are many factors due to which these distortions takes place, such as we can say sensor position, or due to the curvature of the earth's surface, and even due to the various terrain reliefs. And actually, when we are talking about the satellite rectification, first you should understand what is rectification. So when we are talking about rectification, it means it is the process of transforming the image in order to remove its distortion and then align it with a known projected or coordinate system. Means distortion are removed, all the distortions of the images, geometric distortions of the images are removed, and then it is aligned with a particular standard projected system, or we can say coordinate system. So let us take the example. Consider a satellite. Here just you can find, consider a satellite image which is captured over the mountainous region. The terrain relief causes various types of distortion, maybe perspective distortion, or maybe we can say some sort of distortions related to the projections, terrain relief, etc. So these distortions are also caused due to the elevation effects, I can say. So the terrain relief causes these geometric distortions, such as perspective effects, elevation variations. Though the geometric transformations, the image can be rectified to correct for this distortion, ensuring accurate spatial relationships and measurements for application like, I can say, land cover mapping, you can take, or even for environmental monitoring and urban planning, etc. So this is what we can say. Here you can see on your slide, student, land cover mapping, environmental monitoring and urban planning means after rectified image. These are the different applications where you can use this images. Now coming to the another type of example, that is georeferencing the historical maps. Historical maps mainly which are obtained or drawn before the widespread use of standardized coordinate systems and the map projection, they were lacking in the precise reference information. Georeferencing is the process of assigning a spatial coordinate to the points on the historical map and then aligning it with a modern reference map or data set. Means whatever the historical maps which is not referenced, those maps are aligned on the modern maps in order to reference those historical maps. So let us take the example, students. You can see here one of the historical map on the screen. Suppose you are having a scanned copy of some historical map that may be representing city from the 19th century. Then by georeferencing this map, you can align it with a contemporary map of the same area. Means the recent map or the referenced map of the same area, such as digital or we can say orthophoto or into the GIS dataset. This involves when the historical map that is not referenced, that is aligned on the contemporary map, then here now we are going to identify some common features on both. That common features may be in terms of the some roads or we can say intersection points, many times the clock tower, etc. What may be the or some type of important landmarks. The common features on both the maps are identified and using the geometric transformation to match the corresponding points. Once georeferenced, the historical maps can be used for spatial analysis, maybe for the cultural heritage, preservation and studying changes in urban morphology over time. So this is what we can say, this is another type of geometric transformation, that is georeferencing the historical maps. So second types of transformation now we are going to discuss here, that is coordinate transformation. Now coordinate, once we are dealing with the coordinate transformation simply involves here the conversion of coordinates from one coordinate system to the other. Simply if we know that the spatial data are generally acquired from the different sources, maybe sometimes satellite imagery, aerial photographs, drones, GPS, or we can say a number of sources. Suppose one of the data is having a different coordinate system as compared to the other data, means what in coordinate transformation actually we do, we transform one type of coordinate system to the another type of coordinate system. So let us take the example GPS navigation and the parcel mapping of land surveying. So these two example we will take to understand coordinate transformation. So GPS navigation, when we talk about the GPS navigation, we know GPS devices are generally used, GPS devices use different latitudes, longitude coordinate system which is known as geographic coordinate in order to determine the position of a receiver on the Earth's surface. Suppose we are having any GPS, then what that GPS will do? It will identify our latitude and longitude on this Earth's surface. That is what actually the work GPS do. Now, however, the maps and the navigation system we are using, that often have the projected coordinate systems, maybe universal transverse marketer, that is known as UTM system. Maybe it may be following state plane coordinate system, that is SPCS, or local grid system for more accurate distance measurement and map representation. Now, what we have to do? Let us understand in this GPS navigation what types of transformation actually takes place when we use GPS, a navigation app on our smartphone. We know nowadays everybody is having this smartphone. Then we use the GPS in that for GPS navigation app on our smartphones in order to get the driving directions. The app receives our current location as geographic coordinates, means latitude and longitude, through the GPS app, we can say, from the GPS receiver. So our location is recorded in terms of geographic location, that is latitude and longitude, by the GPS receiver. Then this app performs coordinate transformation in order to convert these geographic coordinates, means our position which is obtained as a geographic coordinate. Then this app actually transforms to the projected coordinate system that is used by the digital map. So digital map is actually using projected coordinate system, and our position have recorded in geographic coordinate system. So this geographic coordinate system will be transformed through this app to projected coordinate system on the map. So this transformation allows the app to display our location accurately on the map and then calculate the distances and provide turn by turn the directions based on the projected coordinate system. So such type of transformation can be seen, such type of coordinate transformation can be seen during the GPS navigation. Coming to the another example, this is parcel mapping and land surveying. Parcel mapping, actually it is related to the property when we use to measure, when we use to know the position of different property boundary, etc. Actually this is parcel mapping and land surveying is used by the land surveyors, and they use the coordinate transformation in order to accurately represent the parcels, or we can say the boundaries, property boundaries on the maps or either on the legal documents. The survey measurements are often collected in the field using GPS, and nowadays it is also the survey points are generally recorded with the use of total, we can say total stations. These are also because they give more accurate results. So either it can be recorded through the GPS or we can say the total stations, and then it is reference to a local coordinate system, means that recording is taking place in a local coordinate system or survey control points. Now these measurements are needed to be transformed to a standard coordinate system in order to have a better compatibility with the cadastral maps and the property records or either with the GIS data sets. So transformation is must part. Let us understand with the example of parcel mapping. Here a land surveyor generally conducts a boundary survey for suppose a land surveyor is conducting a boundary survey for a new housing development using some GPS equipment in order to collect the coordinate data for the property corners or for the property boundaries. The survey data is initially referenced. What the data is we are getting during this boundary survey or we can say property survey, the initially reference a local coordinate system. The data is generally referenced to a local coordinate system that is mainly established by that project area. So before finalizing it, what the surveyors do before finalizing the report or the property plots, the surveyor performs a coordinate transformation in order to convert the survey data from the local coordinate system to the standardized coordinate system. And that standardized coordinate system may be state plane coordinate system, that may be SPCS, that is state plane coordinate system, or it may be transformed to some global datum reference, we can say like WGS 84. Reason? Because this transformation, firstly it was recorded with reference to the local coordinate system, then it was transformed to some standardized projected coordinate system, maybe SPCS, what I have said, that is state plane coordinate system, or some global datum like WGS 84. So actually this ensures the survey measurement are generally compatible with the existing cadastral data, property records or GIS layers maintained by the government agencies or either by any, we can say, land management organizations. So that's why we can say coordinate transformation also play a very important role. So after completing the geometric transformation, coordinate transformation, the third type of transformation is topological transformation. Whenever we talk about the topological transformation, it involves altering the spatial relationships and the connectivity of the, we can say, spatial entities, objects, features. Means it actually transforms, alters the spatial relationships and the connectivity of the features while it preserves the geometric shapes. So here we are going to take examples in order to understand this. Means alterations are taking place in topological transformation. Means transformation itself means some sort of manipulation, some sorts of changes, some sort of transformation is taking place. So here actually the transformation of spatial relationships and the connectivity is taking place, but the geometric, we can say, geometric shapes are generally preserved. Let us understand by taking here two examples. You can, first one is network simplification in transportation planning and another one is polygon overlay in environmental management. So first, network simplification and transportation planning. Here actually, transportation networks such as, we can say, road networks or public transit systems are often complex, we can say. Whenever you must be, when you want to travel, you must be seeing the map also, and you are saying n number of routes that you can reach the destination through this route, or n number of routes. So actually transportation networks such as, we can say, road networks and the public transit systems are very much complex and detailed. So in order to simplify this complex networking in transportation, actually in transportation planning, it is common to simplify these networks in order to improve the computational efficiency, because so many times we generally overlay, many times it is used for the Google Maps and all. So we generally use to simplify these networks in order to improve its computational efficiency or even to abstract them for high level of analysis. So let us take the example. You can see here, this is one type of, you can see on the screen, student, this is one type of network and this is the second one is another type of the network, you can see here. So the previous one, first one is very much complicated, and we can say the another one is a bit simplified one. It is a bit simplified. So consider what I have shown in previous slide. Just take this. So here you can consider a city network which consists of numerous interconnected streets. So just consider any of the city network which consists of n number of interconnected streets, intersections and the highways. In order to model the traffic flow or analyze either the accessibility, it is very much useful to simplify this network by reducing it to skeletal representation. Means why I am calling that more complex network is simplified and represented as a skeletal representation. That will, because that will only consist, means when we are simplifying, it means we are reducing the several minor connections, minor networks, minor roads. Only the major roads and key junctions were preserved. So actually in this topological transformation involves removal of the minor roads and simplifying the complex intersection while preserving the essential connectivity and spatial relationships. The simplified network can then be used for various purposes. Just like you can see here, it can be used for route planning, traffic simulation or urban transportation or modeling. So it can be used for various. Now, second example, here we are going to take polygon overlay in environmental management. polygon overlay. I have talked lot about the overlay. If you remember, students, overlay simply we are giving the different input layers, different information one upon the other to know the intersection points and to know the overlapping points in order to get some useful information, in order to have some smart decision making. So here polygon overlay, we are going to give the example that is related to the environmental management. Actually, polygon overlay is also known as spatial intersection or union. Why spatial intersection? Because different layers are overlaid, intersected and united. That's why it is known as the, we can say, spatial intersection or union, which involves combining, or we can say merging multiple layers of polygon in order to identify some sort of spatial relationships and overlapping areas between the features. So let us take the example here. You can see here in this map, students, different layers have been taken, some in which the common areas, biodiversity, high priority areas are mapped. So let us take the example. Suppose what we do in environmental management, the conservation planners often use the polygon overlay to assess the habitat suitability. Here we are dealing with the environmental management. So what the conservation planners do, they overlay or assess the habitat suitability, and in order to identify the protected areas, and for that in order to, we can say, prioritize the conservation efforts. For example, consider a conservation project which mainly aims on identifying the areas of high biodiversity value, and that will be done by overlaying the habitat distribution maps. Means one layer will be of habitat distribution layer, another layer may be of ecological corridors, and we may also have the layer of land cover data. So here we are taking multiple layers, means layer of habitat suitability. For this we are considering in order to delineate the high biodiversity value area. Here we take the habitat distribution map, one layer, then the ecological corridor, and then the land cover data. Now the topological transformation involved in this process will include intersecting the habitat, because habitat distribution map we have taken the first one, so the habitat polygons with the ecological. Second map we have taken the ecological corridors. So actually the in this type of topological transformation, first the intersection of habitat polygons with the ecological corridors will be performed in order to identify the critical wildlife corridor. Then uniting the result of this polygon, which is obtained by the intersection of these two layers, we can say, that will be again overlaid by the land cover data in order to assess the habitat connectivity. So first one, we have identified the critical habitat wildlife, and then the habitat connectivity have been identified just by determining the overlap with the existing protected areas in order to identify the gaps. What are the gaps that is existing, we can say, for the conservation coverage. So this analysis will help, actually it will help to prioritize the conservation actions and then allocate the resources effectively in order to protect the ecologically important areas and the species habitat. So actually thus we can go for the environmental management, and thus our conservation efforts will be prioritized. So coming to the another type, that is the raster transformation. Raster transformation. What is, we have studied what is vector data and what is raster data, what is vector, what in raster. So here actually the raster transformation, it simply means modifying the raster data sets through the operations such as resampling, reprojecting, or we can say geometric, or maybe through the geometric adjustment. Means resampling, we are transforming raster transformation through the resampling, reprojecting, or even we can say through the some sort of geometric adjustment. So this will we are going to understand here by taking the two examples, satellite image orthorectification and digital elevation model resampling. Let us take the first one, satellite image rectification. So generally the satellite images are often we can say obtained which suffers from the various type of geometric distortions due to the various factors like many times due to sensor orientation, or we can say earth curvature, or even through the terrain relief. Due to these factors, many types of geometric distortions are seen. So actually the orthorectification which I am going to talk about here, the satellite image orthorectification. Orthorectification is the process of geometrically correcting the satellite images in order to remove these distortions what we talked about. So in orthorectification we simply remove the distortions and make that image compatible with the map projections or some ground truth we can say. So let us take the example here. When satellite images are acquired, I have already said they contain various types of distortion, maybe through the satellite position, altitude, sensor orientation, I can say, etc. Sensor characteristics, many times sensor characteristics may also cause certain types of distortions. So orthorectification involves rectifying these distortions by referencing them to a digital elevation model, the pre-existing digital elevation model, and then applying the correction for terrain relief and sensor geometry. So this process will ensure that the resulting images is that much accurate up to the scale, shape, or even we can say spatial registration. So actually the ortho-rectified images then that can be used widely in different applications such as land cover mapping, environmental monitoring, urban planning, and natural resource management. Another example you can take digital elevation model. In this other than orthorectification, here we are going to do the resampling. Actually the changing the spatial resolution of digital elevation model for the consistency, because we know the DEMS, that is digital elevation model, represent terrain elevation data as a grid regularly spread, because we are talking about the raster, means that actually the digital elevation model, these models represent the terrain elevation data as a grid which is regular, because grid is regularly spaced elevation values, and these DEMS may have different spatial resolutions which can affect the level of detail and accuracy in terrain of it is but obvious if you are having the different spatial resolution, so it will affect the accuracy in the terrain representation. So what we do in this resampling is actually the processes where the changing the spatial resolution of a DEM by interpolating the elevation values in order to create new grids with different cell size. Interpolation, suppose some of the values, known values we are having at certain points, then with the help of this known values, the values of unsampled points and unknown values are generally calculated, that is known as interpolation. So just consider a project that requires integrating the DEM data, digital elevation model data, from multiple sources having the different spatial resolution, means its accuracy will be affected because the sources from data received from the different sources is having different spatial resolution. So in order to ensure the consistency, accuracy, and the compatibility, the digital elevation models needs to be resampled in order to have the common spatial resolution. This will involve interpolating the elevation values to generate a new grid, means interpolation, that is simply by the known points we are calculating the unknown values. So this will generate a new grid with uniform cell size while preserving the important terrain features and the characteristics that will be retrieved, means that will be conserved. All the important terrain features and the characteristics will be preserved, but the new grid with uniform cell size that will be generated. So resampled DEMS now that can be used for the various applications like flood modeling, slope analysis, viewshed analysis and terrain visualization. We can use it for n number of things. Now, here I would like to talk about the attribute transformation. Attribute transformation is actually, we can say this is the last type of transformation. Attribute transformation, here modification of attributes associated to the spatial features is performed. Means modifying the attributes or even the properties, we can say that is related to the spatial features in a geographic, or we can say spatial data sets. Let us understand with some of the examples. Here you can see the examples, that is population density calculation, normalized difference vegetation index calculation. Let us take the first one example, that is the population density calculation. That is population density, that is very commonly used attribute in spatial analysis, which represents actually the number of people per unit in a given geographic area. Now, calculating this population density involves transforming the population counts and geographic areas in a density measure. Means we are creating from voluminous data, we are creating the subsets. Means one data the population counts, another data is the geographic area, then we are combining this, we are getting the density measures. So let us take the example here. Here student, consider any project which is aiming to just analyze the population distribution and density across a particular city or an area. So the population data is generally available in the form of the population counts for the different census tract and the administrative unit within the city. We know, thus we are having the population data. So in order to calculate the population density, the population counts are divided by the corresponding area of each unit, resulting into the population values. Example, people per square kilometer, or even we can say per square mile, whatever the set criteria is for each tract or unit. This attribute transformation then allows the users to identify the areas of high population density, low population density, and then we can make some informed decisions for the urban planning, resource allocation, or for some other public policy. Let us take another example to understand this attribute transformation, that is the normalized difference vegetation index, which in short form it is called NDVI, normalized difference vegetation index. So actually NDVI is what? It is a vegetation index, and it is now very much commonly used derived data, which is derived from the remote sensing data, and which measures the presence of the healthy vegetation, or we can say overall health of the vegetation. So it is calculated based on the ratio of difference between the near infrared and the red reflectance to their sum. So here you can find the equation on the screen, student, the equation NDVI. You can, what I have said, that it is the ratio, we can say the difference between the near infrared and the red. You can see in the sum of these two, near infrared and red reflectance. Let us understand this with a particular example. In agricultural monitoring, NDVI is generally used to assess the crop health, monitor the vegetation growth, and to detect the changes in the land cover. So remote sensing imagery, such as we can say multispectral satellite images, which provides reflectance values of near infrared and red bands, the NDVI values are calculated actually for the each pixels. Means each pixels, what is the NDVI value of the each pixel by applying the NDVI formula, which we have seen in previous slide. Now the resulting NDVI raster represents vegetation density and health, with high NDVI values indicating the better health, more vegetation density. If the NDVI value is low, we can say the less vegetation density, indicating the sparse or some sort of stressed vegetation. So actually this attribute transformation enables the various, we can say, agricultural experts which are very much related to the agriculture science. So they can use this NDVI values or the NDVI transformed values for to monitor the crop conditions, assess environmental impacts, and make some informed decision in crop management and land use planning. So thus we can say transformation in spatial analysis play a very important role, and in this class we have discussed the different types of transformation with various real world example. So that's all for today's class, student. Till then, have a good day. Thank you. Thank you all.